I've got this. Okay, our next named award, the A. Brazier Howell Award. A. Brazier Howell began his career as an ornithologist, but after moving to California as a young man, became interested in mammals as well. An appropriate decision. Howell conducted field surveys on birds and mammals as an employee of the U.S. Biological Survey, and for many years lectured in astronomy or in anatomy at Johns Hopkins Medical School. Howell was a charter member of the ASM and served as president of the society from 1942 to 1944. He generously provided ASM with the endowment for which the award now bears his name. The 2018 recipient of the A. Brazier Howell Award is Casey Day. Casey just finished his PhD at the Department of Forestry and Natural Resources at Purdue University under Pat Zollner. His dissertation research utilized individual-based modeling and population genetics to answer questions about movement, ecology, and functional landscape connectivity for reintroduced populations of American martens in Wisconsin. More broadly, Casey is interested in combining traditional field techniques with simulation modeling to answer questions about animal behavior and conservation. Now, he just finished this degree, and he's moving to start a postdoc at the University of Montana on the genetics and movement ecology of trout in the Pacific Northwest. If you think that his education was incomplete and he doesn't realize that trout are not mammals, he does explain this in that he is moving from working on mammals directly to working on their prey for a stint. We're confident that he's going to come back to mammals. Casey is going to tell us how individual-based modeling of an endangered carnivore can be simultaneously pragmatic and paradigmatic. Let's welcome Casey Day.
Okay, thanks so much for that introduction. I am really excited to be here. It's a real honor to be a recipient of the A. Brazier Howell Award this year. So I'm going to attempt to present a couple of chapters from my dissertation work today. Before I do that, I want to acknowledge my collaborators and funders, especially the Great Lakes Indian Fish and Wildlife Commission that funded a lot of my work, and of course ASM for bringing me here to present my work. So for the last several years, I've been working on American martens in the upper Midwest, northern Wisconsin, and the upper peninsula of Michigan. Martens were extirpated from this region in the early 20th century. Since then, starting really in earnest in the 70s, there have been a number of reintroductions, translocations continuing even through the 2000s. In the upper peninsula of Michigan, the martens have really done well. Their populations are flourishing. There's a harvest season open. In Wisconsin, it's a different story. They remain both state and tribally endangered in Wisconsin. Martens are culturally important. They're important for local Ojibwe tribes. They're a clan animal for those tribes. And they can be an economically valuable fur bearer where they are abundant. So I was interested in looking at connectivity between these reintroduced populations. So if you see here, you've got my study area polygon there in the middle, and then on either side of those you have a reintroduced population of martens. One to the Chequamegon National Forest in Wisconsin in the west, and one to the Upper Peninsula on the east. And in between you have this forested habitat corridor, but most of this area is county and private land, so not a lot of work has been done on martens in the area, but it serves as an important connection between the reintroduced populations. So I was interested in understanding landscape connectivity between these populations, and in addition to that, there's an iron ore deposit that runs right through this space between through this habitat corridor. And here is the footprint of a mine, a taconite mine, an iron mine that was proposed to go in there. That's since fallen through, but mine exploration in the area continues, so I was also interested in how land use change might affect landscape connectivity. So to tackle this question, I wanted to produce an individual-based model that I could use to simulate dispersal between these populations. But to do that, you first have to create a model that actually works and that reproduces actual marten dispersal behavior. So I had two objectives. First was create a model that could actually reproduce empirical patterns of marten dispersal, and then second, to take that model and apply it to a landscape to questions of landscape connectivity and questions of land use change. So in concert with those two objectives, I have two primary simulation extents. So for the first objective, you have the large gray polygon on the left. That's what I use to build and calibrate my model by reproducing patterns of dispersal from data that were collected from translocated martens in 2009 to the Chequamegon National Forest. The red stars represent different release areas for those martens. So that's what I used for calibration, and then I took that model and applied it to the yellow polygon on the right, which is situated between those two reintroduced populations that I mentioned before. So to zoom out a little bit here on individual-based modeling, in 1999, Volker Grimm wrote a review of individual-based models in ecology to that point, and he identified two primary groups of models, those that were pragmatic, primarily pragmatic in motivation or addressing applied questions, and those that were essentially paradigmatic or addressing theoretical questions. And this is not a true dichotomy. There's a spectrum between these two, but Volker's complaint in this paper is that the vast majority of IBMs were concerned about pragmatic issues, applied questions, and there weren't enough people working on using IBMs to advance ecological theory and compare to more traditional ecological modeling. In 2014, DeAngelis and Grimm followed that up with another review, and still most IBMs are primarily pragmatic in motivation, though they concluded that more and more people are working on theoretical questions with IBMs. My question was initially pragmatic in nature. I was interested in understanding landscape connectivity for these marten populations from a conservation perspective. Landscape connectivity can be notoriously difficult to measure. There's a huge literature devoted to it. And when we measure landscape connectivity, we can do that structurally. Often we omit animal behavior, dispersal costs, complex decision making when we look at structural connectivity. Other measures of landscape connectivity assume animal omniscience so that the animal can perceive the entire landscape at once and make decisions based on that information. With an IBM, you can get past some of these limitations by parameterizing individual agents with simple rules that govern how they interact with each other, how they interact with the landscape, and then you set them loose across the landscape and you allow the connectivity across that landscape to emerge from those interactions of individuals with one another and with the landscape. So to build my IBM, I use the SEARCH modeling framework. SEARCH stands for Spatially Explicit Animal Response to Composition of Habitat, a mouthful. The goal of SEARCH modeling is to simulate dispersal behavior, dispersal, home range establishment, and then mortality and also reproduction can take place. So you release animals onto the landscape, and as they move through the landscape, they're responding to 4 independent spatial layers that govern food availability, predation risk, movement, barriers to movement, and then habitat suitability and locations of conspecifics. So on the right, I have an example of the habitat suitability layers. So the tan color represents unsuitable habitat, the green would be suitable habitat, and the purple would be occupied polygons. So a marten moving through this landscape would have to find a suitable area that's also unoccupied by a member of the same sex in order to establish a home range. So for my model, I used a 60-day dispersal window for martens and a 15-minute time step. So I'd love to dive into all the parameterization of the model, but the best I can do for you is to give you just a sampling of a lot of the work that has been done to go into parameterizing this model. And this work has been going on for decades in this region, and I'm standing on the shoulders of a lot of people that have done a lot of work to go ahead of me. If you want to talk about parameterization, I'm sure you can find me at some point during the meeting. So while I was building this model, I followed what's been termed the modeling cycle. And the idea of the modeling cycle is to identify your question, formulate a hypothesis, build the model, and then analyze the results and see if your model is reproducing the behavior that you want. If it's not, then you go through the cycle again, you build a new hypothesis, new model, analyze your results, and you repeat that cycle until your model is performing as you expected. So as I was interested in dispersal behavior, I was testing theories and hypotheses about marten dispersal behavior. So these are color-coded, but the first hypothesis is that individuals can settle immediately. As soon as they disperse or as soon as they're released, if they find a suitable location to establish a home range, they can establish on day 1 if they want to. That model did not work at all. Animals were establishing way too soon and way too close to home. So the next hypothesis that I looked at was imposing this exploration phase on Martens. So I forced them to search their environment for 2 weeks before settling and finding their ideal home range. 2 weeks was the minimum time that we found from our empirical data that it took Martens to establish. This helped improve the performance of the model. Dispersal distances improved, but dispersal times weren't great, and it was hard to get dispersal times and mortality rates to balance. And so I moved to another hypothesis, which was proposed by Ward in 1987, an American naturalist. And the idea behind this hypothesis is that for a disperser that has a limited amount of time to establish a home range, to settle, the quality of habitat the disperser should be willing to accept, to settle in, should decline over time. So at the beginning of the dispersal period, they can be really picky about which habitat they want. They can get the best habitat. But by the end of the dispersal period, they might be willing, for example, to incorporate a clear cut into their home range. So this theory, this hypothesis has support from marine larval organisms, but it lacks any support or testing from vertebrate species. And so I'm only going to, so I matched a lot of patterns, a lot of data, empirical data. I'm only going to show you dispersal distance in the interest of time. But what you're looking at here is dispersal distance on the y-axis. And on the far right, on the hollow bars here, you have empirical data. And this bar represents all empirical data, and this represents empirical data with one outlier removed. So we had one Marten that went 47 kilometers, and the rest averaged like 11 kilometers. So I like to show both the data with and without that outlier included. So the color coding down here matches the hypothesis from earlier. So what you're seeing in the rest of these bars are different parameterization sets or different model scenarios. So the green group had that rule where they could establish immediately, and they weren't going far enough. They're establishing too close to home. The blue group incorporated that 2-week exploration phase, imposed exploration phase, as did the red group, but the red one also incorporated that theory of declining habitat selectivity over time. So both the blue and the red did a reasonable job of matching dispersal distance, and we matched not only the mean, but also the standard deviation of the dispersal distances. But the blue group also did poorly in other areas like time to dispersal and mortality, as I mentioned before. But the asterisk represents the best model overall, and this incorporated that hypothesis of habitat selectivity over time, and I was able to match 8 out of 9 of the patterns that I looked at using that model. So after I had my calibrated model, one additional thing that I did was I did this post-calibration test to see if I was getting a reasonable dispersal distance distribution. So these data are dispersal distances from all the replicates of my best performing model, and that's fit to a Weibull distribution, which is a classic dispersal distribution for terrestrial species, and is characterized by a high peak and then a long fat tail. So I was reproducing some of these long distance dispersal events, but just not to the extent and frequency that would have been predicted by our empirical data set. So now that I've got my IBM that is working to my satisfaction, I can apply it to the yellow polygon, which is this other landscape and this question of landscape connectivity. So I was interested in the effect of the mine on landscape connectivity between these populations, but I was also interested in how asymmetry in landscape configuration from each direction affected it. So in my models, in my simulations, I only release animals from one side of the landscape at a time and allowed them to disperse across toward the population on the opposite side. I was also interested in looking at mortality and how turning mortality on or off through predation and starvation in the model could affect landscape connectivity. So for each replicate, I allowed Martens to disperse across that landscape for 5 generations, 10 individuals for each of those generations, 10 replicates per scenario. When I say scenario, I mean each combination of these factors in a factorial design, for a total of 6,000 dispersal events in the landscape. So just to give you an idea of what this looks like across those 5 generations, I released individuals from the eastern portion of this landscape in this case, and over 5 generations, they are randomly dispersing across the landscape, but eventually making their way by generation 5 towards that other population on the opposite side. So to analyze these data, I wanted to look at 2 primary response variables, 1 functional connectivity and 2 dispersal behavior. So to measure functional connectivity, I measured net directional displacement away from the release location, away from the release polygon. So the further across the landscape you go, the higher your net directional displacement is. And I used regression tree analysis to determine what factors had the biggest impact on functional connectivity. Then I also looked at dispersal behavior metrics like dispersal distance, time to settlement, and dispersal success. So for functional connectivity, as I mentioned, I use regression tree analysis. And if you take all the data from all dispersers and put it into a regression tree, the results are not very interesting. If you're not familiar with regression trees, every time you have a split, that indicates that there's a significant effect of the variable that's identified in the split. In this case, it's mortality. So there was a significant difference between when mortality was on and off in the model when you include all data. But to me, it doesn't really make sense to include all data in a measure of functional connectivity because connectivity is really driven by those long-distance dispersal events, the tail of that distribution, as I mentioned. So I started looking at subsets of the data, and if you look at just the top 25% of the data of those individuals that moving across the landscape, you start to see an effect of the mine, the no mine versus mine included scenarios as well. And if you look at just the top 10% of individuals across the landscape, you also start to get an effect of direction, west to east versus east to west, that WEW, and asymmetry in landscape configuration. And then if you just look at the top 1% of individuals that made it across the landscape, you see an additional effect of direction when mortality is turned on. So one thing I want to point out is that whenever mortality is off is primarily when you're getting these effects of other factors as well. And that's not how it works in the real world. In the real world, mortality is on. And when mortality was on in my model, I didn't see much effects of the mine or of asymmetry in landscape configuration. So for these dispersal distance metrics, again, the dispersal behavior metrics, I'm only going to show you dispersal distance. And so you've got dispersal distance on the y-axis and you've got the mortality on the x-axis. And what I want to point out here, just the general trends, that among different mine scenarios, you don't have much difference in dispersal metrics. That includes the other metrics that we looked at too. But you did see differences in mortality and in direction. Often there was an interaction effect between mortality and directionality. So to try to wrap all of this up, my initial motivation for building my model was pragmatic. But over time, I switched to investigating theories of dispersal behavior, and my approach became more paradigmatic, and until my model was ready to apply to that more pragmatic application. But my point here is that I may not have been able to answer the pragmatic questions without first taking a more paradigmatic approach or a more theoretical approach to individual-based modeling. And I think we're seeing more and more of this. I'd love to see more of this type of modeling at ASM in the future. I did find support for Ward's hypothesis of declining habitat selectivity over time. This is the first real empirical evidence for a vertebrate species, so I think more investigation is warranted for that hypothesis. In terms of functional connectivity, mortality had the greatest impact. And a lot of times in studies of landscape connectivity, we omit mortality and we just look at the structure of the landscape, but it's an important factor that can prevent populations from being connected. Dispersal behavior is not a surrogate for connectivity, so things like dispersal distance, time to settlement, you can't just look at those variables and assume that a landscape is connected or not. My response variables or explanatory variables had different relationships with functional connectivity versus dispersal behavior. And then finally, the impact of the mine really only had an impact when mortality was turned off in the model, and it had almost no impact on dispersal behavior. And that may be because the mine was stuck right in this huge chunk of contiguous habitat. So while there was maximum habitat loss, it seems that there was not a lot of effect on landscape connectivity, actually. So I just want to make a sales pitch for IBMs here. IBMs are a great tool for furthering understanding of your system and really understanding the processes that are going on in your system. They're becoming a lot more accessible, a lot easier to produce. NetLogo is an IBM software that's really easy to learn, and there's a great book that'll, if you've never written a line of code in your life, you can get this book and you can start building IBMs on day one. There are also workshops available, but as I said, I'd love to see more and more IBMs popping up at this meeting too. So thank you so much for your attention.
We do have time for a question or two.
Theoretical modeling on dispersal in Martens, but their intersectional territoriality has suggested that females should be more concerned about finding a site to colonize that doesn't have any other conspecifics, whereas males should be looking for females. And we've recently tested that on fishers and found an actual difference. Females, when they can disperse across the landscape, are looking for a place that has no other fishers. And then males superimpose on top. Did you look at sex effects in your modeling?
So the question is about mustelid patterns of mating and how males in the mustelity tend to look for females when they're establishing home ranges, and females tend to look for areas that are unoccupied by any individual. In my simulations, females, the only effect on sex is that you can occupy an area that's occupied by a member of the same sex. Females could occupy an area that's already occupied by a male. That would be an awesome question to look at next. There's always the next question. There's always, adding more realism into a simulation model. And right now, the framework of search is such that functionality doesn't exist yet, but that would be a really interesting avenue of inquiry. Thank you.
We better stop there. By the way, if you're going to address that question, it's not going to be in trout. just so you realize.
No comment.
Thanks, Casey.